In this video, we'll move into section 1.6 and discuss the formal limit laws. These will be our key to solving the equations when we're trying to evaluate limits and we're given the equation instead of the graph. But just before we jump in, I want to go back and take a look at one more, doing the numerical approach to try and evaluate a limit. So I've got a problem here. The limit is x approaches 0 of the function minus 4 over x squared. And just like we did in the 1.5 video, with our equations, without any more rules or understanding, I'm just simply going to make an xy chart. I'm going to pick a bunch of x's that approach 0 from both sides. So from the left, I'll pick negative 0.3, negative 0.2, negative 0.1, and I'll probably also do negative 0.01. Again, just showing we could really keep getting closer and closer to 0, negative 0.001 if I needed. And from the other side, I'll do positive 0.3, positive 0.2, positive 0.1, and positive 0.01. And just like I did in the other video, certainly this is not that bad to plug in by hand on a scientific calculator, but I'm gonna again take advantage of my graphing calculator. And again, not to worry if you don't have one. As I keep saying, this is a nice technique, but this is really a little bit of a long way around. Some people just like this as a method of check. And as we get through 1.6, we'll realize some of the little shortcomings that come with this, but overall still reiterates the intuitive idea of a limit. Picking x values that approach the x we care about, seeing what's happening to the y's. Okay, but now let me put it in my calculator, so I'll clear my previous function. Negative 4 divided by x squared. And I already have my table set up from the other day, so I could just go right to here, pick my new x values, negative 0.3, and I get negative 44.44. Negative 0.2, and I get negative 100. Negative 0.1, I get negative 400. And just like I said the other day, I'm going to stop right here. Maybe this is close enough to get the big picture, so now I'll start looking at approaching 0 from the right, but then we'll come back and look at these last two if we need them. So I'll look at positive 0.3, and I get negative 44.44. Sometimes there are some coincidences. I'm getting the same value here. Other times, like the other video, we had one where we were equally apart from our point where the y's were coming together. But again, it's just seeing what's happening. These are becoming bigger and bigger negative y values. On the other side, positive 0.2, positive 0.1, and I'm still getting those same values. So looking from both sides, my y's doesn't quite look like I'm honing in on a single y value, but I notice the trend is that I'm getting bigger and bigger negative y's. Fairly big negatives as well. But maybe I still need a little bit further. So again, let me get these last two. Let me put in negative 0.01, and I get negative 40,000. And then the same thing, if I put in positive 0.01, I get the exact same thing. So this is the big reason I wanted to do this one, everybody. This is still reiterating exactly what we did in the previous video, but just looking at the end. Where are these going? What are they heading towards? And in this one, the trend, these are becoming massively big negative numbers. Again, you could still keep going. If I put 0.001, I get negative 4 times 10 to the 6th power. I mean, these are becoming massive numbers. These are approaching a negative huge number, and that is the concept of negative infinity for this final answer. So, again, nice little work. The book did bring this up in 1.5, and I probably should have done that in that video. So just a quick reminder, calculator helps whether we get a nice answer like 1, or a fractional decimal answer like 1/4, or an infinity. These charts can still work pretty well. But now, really getting into the new section. 1.6, we start off with a bunch of limit laws. And all I want to do, I already have them written out. I want to quickly summarize what they're trying to tell us. We still don't have the formal definition to prove the first bunch, but we could still explain what they're telling us, and this will connect with our big picture. What are we looking to do in these different situations? How do we handle limits when we are only given the equation and don't have the graph to look at. So that's the direction where we're going. Okay, so what are these limit laws? Well, first we have some given information. Given, and notice both of these limits are approaching the same thing as x approaches a, but here I've got a function f of x, here g of x, and that this limit value equals L and this one equals K. So if we have those facts, now look at how we can build. Law number one says, if now we're not just taking the limit of f or g, but taking the limit of either f plus g or f minus g, but again, notice still x is approaching a in this problem, in this definition, and that'll be true for all of these as we keep going down. We're always going to keep that same a. So the big picture here is, if we're adding two functions and we're taking the limit, all we need to do is add those two values at the end. So if we knew the limit of f was 10 and the limit of g was 6, well then the limit of f plus g would be 10 plus 6, or 16. And the exact same thing happens if it's a minus. If it's the limit of f minus g, we would have gotten 10 minus 6, so we would have got a final answer of 4. So hopefully, this is kind of what we would hope in a lot of situations. What would most make sense, but is that also mathematically possible? And in this case, it is. If we're just adding two functions that we already know the limits of, well, we could take the limits separately and then add the answers. Number two is very similar. C here is just some number. C is just some scalar here. So if I have C times my function f, well then I take the limit. In essence here, the idea is that this C, this multiplier, just pushes along. So again, if we knew the limit of f was 10, but now I want to know the limit of negative 3 times f, my answer would be negative 3 times 10, or negative 30. Well, what if it's not just a multiplier? What if I'm multiplying two functions? Well, same idea. In essence, all this is telling us is that we could just keep taking the limits separately, and whatever operation is connecting these pieces, we just do that to the answers. So now, if I had, again, I think we said the limit of f is 10 and the limit of g is 6, well then now I get 10 times 6 if I'm multiplying f times g in the limit, and that would give me 60. Well, if we multiply the answers. In number 4, if I divide, well then I divide the answers. This will be our big caveat, everybody. In math, what's one of the big things we can't do? We can't divide by 0. So this limit rule works so long as we're not dividing by 0. If we do hit 0, that's where it just takes a little extra. We got to work a little harder. We need a little bit more to figure out that answer. Okay, the book has these, I think they actually do these as two separate ones, but this is the essence of what we get in the book. They bring up number 5. It's really just an extension of number 3. If I have a function that's now raised to a power, well then I just take its limit to that same power. But honestly, that's really just this applied. If this is f of x cubed, well that's really just f of x times f of x times f of x. It's just a repeated use of this. But it's nice enough that it's worth pointing out, writing as its own separate limit. So these are truly our limit laws that we are going to apply, but now we need some information to get started, and that's where numbers 6 and 7 come in. 6 and 7 are going to be the keys that we could use these limit laws and build on, and this will get us to our basic technique. When we have an equation, how do we handle taking limits? We're almost there, everybody. Just got to give me a few more minutes to finish this explanation, get a little bit more of the understanding, and then we can apply everything we're seeing here. So, here, what this is telling us, there's no function here, it's just a number. So the limit of a number by itself, the limit of a constant, is just that constant. And here, if my function is just a plain simple x function, y equal x, well then the limit as x approaches a is just the a value. Let me take one moment. This is not exactly a formal proof, but just to demonstrate why both of these are true, and then we'll get to see how all this comes together and how we use this. So for number 6, let's just pretend we're looking at the function y equals 2. And I want to know what is the limit as x approaches a. I don't even care what that a value is for this function. And the way I'm going to do this is I'm going to think about the graph. We've already seen just the intuitive definition. As long as we see the graph, we could figure out what our limit values are. So what is the graph of y equals 2? It's just a horizontal line that goes through the y-coordinate 2 everywhere. So everywhere going left and right, but never going up and down. And now, it doesn't matter what a is. If a is 1, approaching 1 from the left, 1 from the right, well, all these points and all these points are honing in, coming together at a y value of 1. Well, what if I went out here to -2? From the left, from the right, these points, still lining up with y equals 2. So again, not just for y equals 2. If this was y equals 5, my line would be up here at a y value of 5, but the same thing would happen. So it doesn't matter what a value we approach, this function is always stuck on that number, so it doesn't matter what you approach, you just get that same number back. Okay, now number 7 is a little bit similar. But here, instead of just a generic y equals 2 or y equals -1, just picking one of those examples and realizing how it would work in all cases, now we've got a very specific, let's look at the function y equal x. This has the form mx plus b. The b is 0, so it goes through the origin as its y-intercept. The m value is 1, so 1 over 1, up 1, over 1 as we move along. And that gives us this function. I've got a few marks down. Again, it's a rough sketch, but this will do. So now, once again, let's think about a generic a. And if I start off by letting a be 1 as x approaches 1, so from the left, from the right, these points, coming together at that same value 1. If I let my a value be 2, approach from the left, approach from the right, I'm looking at these points and these points, once again coming together, this time at a y value of 2, so I'm not getting the same limit here with this x as I did here with this x, but I'm still noticing that the limit value here matched the x value we approached, and that same thing happened here. And one more time, even if I did it over here, approach -1 from the left and from the right, these points and these points coming together right here at -1. So again, not a formal proof, just a little generic use of this. And now we can go back and we can take a look at a limit problem we've already done. So we'll keep reminding you of these limit rules, but now let's get a fresh sheet of paper and let's revisit a problem we've already done. Let's evaluate the limit as x approaches 2 of x cubed minus 5x plus 3. Now, if you don't recognize it, we did this at the end of the 1.5 video. I made an XY chart and we figured out that the answer was 1. But now, realizing the limit laws that we have, let's see what we can do here. Now, I'm just doing this one time. You don't need to memorize these limit laws by number. You're not going to need to quote which limit law you're using. Again, this is just trying to demonstrate why these limit laws give us what we need and point out what our technique really is. So if I want to take this limit, I'm going to start off by using limit law number 1 twice. I've got this is my f minus this is g, and technically this would be a plus h, so I could break that up. I could take the limit of x cubed minus the limit of 5x plus the limit of 3. Oops, plus the limit of 3. And now that I've broken this up, for this is basically applying rule number 7 combined with rule number 5. I'm going to start off with rule number 5, that I could take the limit of x cubed and make it the limit of x, quantity cubed, and now I've got the limit of plain old x as x approaches a, so that equals a, and the cube is still there, so that whole thing gives me an 8. For the second part, the minus stays there, and then the 5x is like limit rule number 2. 5 times f of x, the 5 can be kicked out in front, and I'm left with the limit of x. And once again, I'm using limit rule number 7. The minus 5 hangs out. The limit of x, as x approaches 2, is 2. So I end up with minus 5 times 2, or minus 10. And then last, this piece, this is limit rule number 6. The limit of a number by itself, it doesn't matter what the a value is, the limit of a number by itself is just that number. And now, of course, at the very end, let's clean up our arithmetic. 8 minus 10 plus 3 gives us that same exact matching one. So maybe, I can't say exactly what was going through your head, but when we were making that XY chart, and after we got that answer of 1, I think there's definitely a distinct possibility you were thinking, well, why didn't I just plug in 2? If I plugged in the answer, the x value of 2, I got a y of 1, and that's exactly what the answer is. And that's what I was saying in that video. This one, we're not going to need to do this anymore. That's the end game. That's the point. Now that we've done all this once, we don't have to do it again. Our first technique for evaluating limits is just going to be plug in, do the work. And as long as we don't get in trouble, that's our answer. So if I had the limit as x approaches negative 1, and I had 4x cubed minus 7x all over x squared plus 1, that looks quite big and messy, and we could do the whole XY chart, but let's start off just plugging in minus 1. And as long as everything's okay, what's not okay, basically so far the only thing we've seen is as long as we don't have division and divide by 0, we're okay. And that's going to work like a charm here. I'll get 4 minus 1 cubed minus 7 times minus 1 all over minus 1 squared plus 1. Again, formally, I'm using limit rule number 4 to break up the division, then limit rule 1 on both the top and the bottom to separate the addition subtraction. So all those rules, but that's what I was saying at the beginning. We don't have to memorize all those rules. We have to understand what they're telling us, and what they're telling us is we can plug in and try and do this. So let me finish. Minus 1 times 4, I get a minus 4. This becomes a plus 7, so we get a positive 3. And on the bottom, minus 1 squared is 1, plus 1 gives me 2. So we got, 3 over 2, 1.5, 1 1/2, whatever you prefer. So again, a very quick and effective approach. Much better than making an XY chart, much better than getting all the XYs set up on both sides. But now, we're going to hit a little bit of a snag, because in number 3, I'm going to reverse the second problem we did at 1.5. We did x minus 2 over x squared minus 4. I'm just going to reverse it, but then after we finish this one, I'll flip it back. So just like we started with number 1, a repeat of a problem we've seen before, we'll come back and do that again here with number 3. But just first things first, I try and plug in, but when I do that, I get 4 minus 4 over 2 minus 2, and I get 0 over 0. Now we've got some trouble, okay? And this is going to be one set of trouble, and before I even finish this and point out how we're going to work our way out of this trouble, again, we're going to flip this one and see it just like we did the other day, but I also want to start off with the one we literally just started today with, this video. Minus 4 over x squared, as x approaches 0, if you just directly plug in, you get minus 4 over 0. Both of these have divide by 0. Both of these are trouble, but they're going to have different outcomes because of the top. This is what we are going to consider a k over 0, where k does not equal 0, but we're getting something divided by 0. This is trouble. And if you follow the work from the book and look at what happened in our example that we did, this leads to infinity. K over 0 is always going to go to some infinity, but we have to figure out which infinity. And it might be both. So if it's going to positive infinity on one side, but negative infinity on the other, that ultimately leads to a limit that does not exist. So having a 0 in the denominator is trouble, but it's not the worst trouble. How do I figure it out? Well, in this case, I do have to check both sides. I'll let x approach 0 from the left and from the right. But all I'm doing here is testing the sign. Okay, I know the answer is going to infinity. I just need to know, is it positive or negative infinity? So what I do, I pick a value that actually does approach my limit value. So here, 0 from the left. But I don't need to do all the arithmetic. I just need the sign. So if I plug in negative 0.1, well, there's nothing to plug in the top. Negative 4 is always going to be negative. But then in the bottom, I square that negative 0.1 and I get a positive. And a negative divided by a positive is a negative. So from the left, I know I'm getting negative infinity. And now I'll test that from the right. If I go 0 from the right, now I'm thinking about positive 0.1, but I still get a negative in the numerator, and positive 0.1 squared is still a positive. So I'm getting the same situation, a negative over a positive. So once again, I'm getting negative infinity. And that's why this answer is negative infinity. So that's our k over 0 situation. Now, if I only ask 0 from the left or 0 from the right, you wouldn't have to do both. But if you just ask for the regular limit, we have to remember that we have to consider both sides. And again, there is a definite possibility, if you remember from pre-calculus, most of your vertical asymptotes, because that's what's happening here, most of your vertical asymptotes have that going up on one side and down on the other. It's a little less likely to have both going up or both going down. So this was kind of nice. Still, going to come back and look at number 3, but let's stick with this for one more moment. Let's jump into number 5. Let's take a look at the limit as x approaches 4 of 3x minus 10 all over, let's do 4 minus x. So just like the previous one, again, let's make sure, just looking at x approaching 4, I'm going to consider on my own what happens when I approach 4 from the left versus 4 from the right. And now, this is where it's another important spot. If you say what approaches 4 from the left and you say 3, you go to the top and you go 3 times 3 is 9, 9 minus 10, and you get a negative. No good, everybody. You gotta be closer. At least something like 3.5, but 3.9 would be even better. So 3 times 3.9 is a little less than 12, and 12 minus 10 gives me a positive. So just to be careful with that. Sometimes you get lucky. On the other side, if I pick 5, I won't have that issue. But sometimes it's not about when and where you get lucky. Let's know the right way, and let's make sure we're approaching from close distances. So 3.9 times 3 minus 10 gives me a positive, and 4 minus 3.9 gives me a negative. So from the left, we're going to negative infinity. From the right, now I'm thinking about 4.1. 3 times 4.1 minus 10 will still give me a positive. But now in the bottom, 4 minus 4.1, that will give me a... Oh, I'm sorry back here. I made a mistake here. 4 minus 3.9 gives me a positive. I'm very sorry about that. 4 minus 3.9 gives me a positive. So from the left, we approach positive infinity. And now this is correct. 4.1, 4 minus 4.1 is a negative. So from the right, we get negative infinity. And now ultimately, this limit does not exist. We knew right off the bat. I plugged this in, and right off the bat, I got 2 over 0. I'm so sorry I jumped into this. I really should have started pointing that off right off the bat so that I knew I had a k over 0. I knew I was shooting off to one of the infinities. Which infinity? Well, here we're going to both infinities. So that's a does not exist. But if we got the same infinity, that would be our answer. If right off the bat, we only looked about approaching 4 from the left or 4 from the right, we got an answer for each side. But the fact that we had to check both sides and we didn't get the same answer, that's why we ended up with it does not exist. So that takes care of our k over 0. Again, we'll get another video that'll do some overall review or a lot of these concepts, but that's just our first piece. That takes care of the k over 0. And now I want to move right into our next aspect, the 0 over 0 piece. So back to number 3. And now what some people might already be thinking, they're already jumping ahead, and I'm going to give myself some more room. I'll come back and finish this here, but to make my point on what's happening here. There are people who look at x squared minus 4 over x minus 2, and they're already jumping and saying, hey, look, I could factor that. That's x plus 2 times x minus 2 all over x minus 2. Matching factors that cancel. This equals x plus 2. Algebraically, what you are saying is correct. But as functions, if this is my function f of x and this is my function g of x, these functions are virtually identical, but not identical. As functions, this one has a full domain. You could plug any x value you want in here and you'd get a y to go with it. So the domain for g would be all real numbers. But for f, just like we're seeing with limits, when we talk about domain, 0 in the denominator is no good. So 0 in the denominator, that's trouble. That would be a hole in the domain here. There would be something going on in this function f when x equals 0. When x equals 2. But everywhere else, they'd be the same. Look what happens when x equals 1. In this one, I'll do it for both, we'll get a y equals. And in this one, well, 1 plus 2 is 3, nice and simple. In this one, 1 squared minus 4 is minus 3, over 1 minus 2 is minus 1. I still get positive 3. So when x is 1, I get the same y. When x is 0, here I get minus 4 over minus 2, which would give me positive 2. And over here, 0 plus 2 gives me 2. And I could keep going on and on and on. These two functions are going to match for every x value except x equals 2. So I'm doing all this to make a big point. The graph of this basically gives us the graph of this. It's just the only thing that's different is exactly what happens at x equals 2, but all the values as x approaches 2, if I started plugging in 1.9, I'd get the same thing. If I plugged in 2.1 in both of these, I'd get the same thing. So the graph of this, which is just a simple straight line, and if I go to x is 2, I'd realize I'm lining up. The graph is coming together and has a y value of 4. And what's the graph look like here? It's the same picture, except this would be an open circle instead of being a filled in point on the graph. So again, algebraically, if you can do this, the functions are technically different, but their limits will be the same. So now we can come back and jump to number 3. And notice, I didn't start by factoring. Number 2, the top could have factored a little bit, but it was irrelevant. Our first technique is to try plugging in the given x coordinate, and it's only when we get into trouble that we have to do more. And that's what happened this time. And now just a little bit more with notation, everybody. Notice, when you plug in the x coordinate, the limit notation drops. But here, this basically told me start all over. This told me my limit was going to one of the infinities. I had to figure out which infinity. Is it the same infinity? But this tells me absolutely nothing. This tells me to start completely all over. And when I do start all over, I have to keep my limit notation. I keep my limit notation until I'm ready to plug in again. But while I keep that notation, we're going to learn that 0 over 0, we need to manipulate the original. And what does that manipulation consist of? Well, honestly, it's whatever we can do. This one, factoring works, so we factor. Once I manipulate in some way, I should be able to then simplify And notice here that once I manipulate through factoring, that allows me to simplify. And then I can try and take the limit again. This is just a little informal set of directions. And you'll see, factoring will not be the only way we manipulate, but we will see that this just always keeps working in a similar fashion. If we're manipulating correctly, things will nicely simplify, and then we will be able to nicely take a limit at the end. And that's what we finish with here. Now, I went through everything, manipulated, simplified, now I try and take the limit again. So now I plug in the 2, and I get 2 plus 2, and I get a final answer of 4. And that's what we saw on the previous page by looking at the graph. So this is, again, our situation when we're faced with a 0 over 0. That's what we are looking to do. And this may seem like I'm nitpicking here, but the notation is important. You need to have the limit of this equals 4. If you just have x plus 2 equals 4, you're making a garbage equation that doesn't make any sense. Now, in your head, you may be following, and that's certainly a good first part of the class, but one of the tough nuances is embracing the notation, not fighting it. So again, when you manipulate, either you do your manipulating off on the side and then come back and rewrite the limit before you take the limit, or you keep the limit while you continue to manipulate and simplify. But that's where you lose it. You lose the limit notation when you're actually taking the limit. Okay, we'll get more practice with that. So let's keep going here. Let's finish this video. We're going to do a part 2 in just a moment, but let's finish this first video with the other example from 1.5, the flip of what we just did. If I had the limit of x minus 2 over x squared minus 4 as x approaches 2. So just like we did with problem number 1, we did this in 1.5, we made an XY chart, and we saw that was tedious, but in number 1, all we had to do was plug in the x value and we were done. That was about as simple as it can get. And by the way, everybody, that works for trig functions as well. You'll notice the book throws a little bit of trig at you, not too much, and then we'll come back and see more of the trig, especially the 0 over 0 situation. That'll come up separately in chapter 2. So all that stuff, the idea of plugging in, that's not just for the nice algebraic functions. That's our first technique anytime we can. So I try plugging in, but I get 0 over 0, so I manipulate, and this is incredibly similar to what we just did. And I give you permission to do this. I'm just doing my factoring work right here. Now I see these cancel, but I still keep up my good habits. I still keep my limit notation. What's left? That x plus 2 is left, but it's left in the denominator. Don't forget you have a 1, technically that's left from the numerator. And again, things have gone well. It manipulated, it simplified. I should feel positive that this is a good spot to try and retake the limit. And now I try and plug in the x value. I get 1 over 2 plus 2. There's the 1 over 4. When we use the XY chart, we were getting decimals, and we should be able to see that was closing in on 0.25. It was at least a friendlier decimal, but here we can see the fraction that goes with it. Okay, and again, the second part of this video, we're going to keep going. We got a lot more 0 over 0 to discuss, and we also have to discuss the piecewise functions.